Hello everyone, and welcome to part 2 of lecture 13 on neuron models. In the previous section of the lecture, we discussed synaptic models and neuron models, and we came to the conclusion that we want to have a neuron model that produces spikes as a function of some state, and we concluded that the appropriate state was membrane potential. Now, in this portion of the lecture, we're going to talk about some increasingly complex models of neurons that attempt to explain behavior we see in biology. The first model we're going to talk about, a class of neuron models, the integrate and fire models. And what they do is they model the neuron as an electric circuit, where they treat the membrane of the neuron as a capacitor, and that the membrane potential is the charge across that capacitor that is charged up by some input current, that when it reaches a threshold, it then spikes and resets the voltage to some predetermined reset voltage. And so we know that when we model something as a capacitor, we know that the rate of change of voltage as a function of time is equal to 1 over the capacitance times the current that is passing through the capacitor. And so in this way, this capacitor integrates all the currents coming into the cell, and the input currents would be the stimulus possibly processed by the synapse model. And so what we see here on this graph is the membrane voltage starting at the equilibrium voltage that is charged up as current is injected into the neuron. And so the voltage increases until it hits the threshold voltage theta, where a spike event is recorded. And now in an actual neuron, we would see that this membrane voltage would continue on in the shape of this dashed line here, which describes the shape of the action potential. But what this neuron does instead is it just resets the voltage back to the reset voltage. It resets the membrane potential back to the reset voltage. And the spike event has occurred, and then the current starts charging up again until as more input comes in, until it once again reaches the threshold and spikes. So this has the advantage that there is a continuous state variable, and it has real-time dynamics, and the state variable is the voltage across this capacitor. It accounts for behavior above and below the threshold, i.e. there's a spike that occurs when the threshold is encountered, and then the membrane voltage charges up before the threshold is encountered. And it's a flexible framework that allows extensions to improve fitting biological observations in the change of the membrane voltage over time. And so now we'll discuss some extensions to this class of model called the integrate and fire model. An example extension is the Leaky integrate and fire neuron model. In the standard integrate and fire neuron model, there's no way for the membrane potential to decay back to an equilibrium potential, which is something we observe in biological neurons, and we would like to capture that in our model. In the integrate and fire neuron, the voltage can only be decreased after a spike when it gets reset. So to address this, we add a leak current that drains the capacitor until it reaches some membrane potential, indicated here by the battery labeled E-leak. Although V equilibrium would also be a possible label. Once the voltage of the capacitor drains down to match E-leak, then there will be no more current that passes through resistor R, and the neuron membrane potential will maintain that current unless there is some input stimulus that is injected into the neuron that causes the capacitor to charge again. And of course, if the current reaches the threshold voltage, then there is the spike event and the capacitor is reset to whatever the reset potential is. So we can express this as an equation shown here, that the rate of change, the product of the capacitance and the rate of change of the voltage of that capacitor is equal to the current that goes through the leak branch plus whatever the current coming in from the input is. And we can rearrange this just to get the R out of the denominator, and we can write this then as tau RC times the rate of change of voltage is equal to the difference between the voltage measured across the capacitor and the leak potential plus the voltage induced by the injected current coming in from the input passing through this resistor. And of course, this tau constant determines the rate of change of the potential across the capacitor. That is possible, both in terms of charging and discharging the neuron in the absence of stimuli. Charging in the presence of stimuli and discharging in the absence of stimuli. So what we have here is a graph. The blue line is the membrane potential, and the orange line is the input current. And this is how this dynamic system changes as the current is injected into the neuron, and then what happens when it stops later in the future here. And we generate these curves by solving this differential equation, this ordinary differential equation, by first setting the input current to be some fixed quantity, the initial value of the voltage to be 0, solving that differential equation, and we get this equation that the rate of the curve that describes the change of voltage is equal to the potential, the leak potential, plus the resistance on the leak channel times whatever that fixed input current, I naught, is, times this term here, which is 1 minus e to the minus t over tau RC. And this is where the tau controls the steepness, or how quickly this capacitance can, or how quickly the capacitor can charge. And we can see that this term here will be, in the case that t equals 0, this E will be evaluated at 1, and so this quantity will be 0. And as t goes to infinity, this term tends to 0, and so this term asymptotes at 1. And so once we hit the threshold, though, the spike, the voltage is reset to 0, and it begins accumulating current again. And then what happens when the input current is taken away? We solve this differential equation with I naught being 0, or I of t being 0. I naught goes away. And then this v term will be delta v, where delta v is the difference between whatever the current voltage is across the terminals and the leak potential. So it's the voltage measured not from this point to this point, but from this point to this point. And we see that this equation is a term where delta v is this potential here. This decays away towards 0, and so this term decays from whatever the voltage was when the current was taken away, this peak point here. It decays gracefully back towards the resting potential, E leak. And of course, as we said, the shape of both this discharge curve and this charging curve are controlled by the time constant tau RC. Now, we can take what we solved earlier, and I should say that these solutions here that give us these curves are called constant current solutions, because we fix a current at some constant value or at 0. And we can use those dynamics to compute a firing rate. And this firing rate gives us a tuning curve, as seen here for different values of the time constant tau RC. And on the right, we have the tuning curve for a fixed time constant, and then with different values of the refractory time period. And so what we can see here is that as we increase the time constant, the firing rate curve is lowered. And this is because it takes longer to charge up to the voltage threshold, so the stimulus needs to be stronger to evoke the same firing rate. Likewise, as we increase the refractory period, we lower the tuning curve. But as you can see, the shape doesn't bend in the way that it does, here in the green line. We see this dynamic is more similar. But still, this puts an upper limit on how much time the neuron can spend firing, and when it can start charging up again. But it doesn't change the dynamics of how it charges. So these curves should look similar to other activation functions we've seen, and particularly I'm thinking about the ReLU function. And that is to say that, at a certain threshold it turns on, and we start getting spikes that increase as a function of the input intensity. But unlike ReLU, we see that these curves are bent, they're not linear. And so they have the advantage of not increasing linearly indefinitely, which is a more biologically plausible solution. So the Leaky term helped us capture the behavior of actual neurons, the decay of the neuron membrane potential back to some constant voltage. Another characteristic of neurons that we would like to model is adaptivity. That is to say, given a stimulus for long enough, the neuron will adapt and slow its firing rate. So we have this graph here, or this plot of membrane potential of a neuron given different input current stimuli. And so what we can see is that there's this pattern that when the current is first applied, spikes happen close together, and then they start spacing out, and then they stop occurring. Close together, spaced out, stop, and this process repeats. And we can see that basically the interspike interval increases the longer the current is applied. So we would like to be able to explain some of this behavior in a neuron. And so the way we do this is we can mimic this by adding an adaptive firing threshold. So whenever the neuron spikes, so here we see this graph of a constant input to a neuron that's turned off at some point in time. The blue line is the charging up is the membrane potential as it changes, given the dynamic equations we've solved for previously. And now we have this green line, which is the spiking threshold that now has its own dynamics. So when a spike occurs, we record the spike, but then we increase the threshold by some quantity, a fixed quantity, it's 1 in this case, and then we also add dynamics to the threshold so they decay back towards the initial threshold value. And so we see a neuron spikes, the spike is recorded, the threshold is increased, the neuron then starts charging again after the refractory period. And while that's happening, the threshold is decaying back towards the initial value. These two curves meet, a spike is recorded, the threshold is increased, the neuron membrane potential is reset, and the process of charging up continues, the process of threshold decay continues until they intersect again. Another spike, and then this starts to decay, and then at this point the current is turned off before the membrane potential and the threshold intersect, so there aren't any more spikes. But what you can see is that the time between spikes is increasing with this particular threshold pattern. And so we've now captured this adaptivity using the Leaky integrate and fire neuron. But this family of neurons, the integrate and fire family of neurons, are not without their failings, right? So if we look at the action potentials here, I mean, they're spikes, right? And they are also, this is the activity. These spikes describe the activity or the change of the voltage across the membrane potential that is enacted by the neuron itself. And what we're doing is we're simply recording a spike if the membrane potential reaches the threshold, right? There is no spike described in this blue line, the membrane potential curve. It's simply a logical comparison. If voltage equals threshold, then spike, and that's covering up a lot of the complexity in the dynamics of the actual neurons. And further, this system is a hybrid between ordinary differential equations and this hand-designed imposed logic we're putting into it. the logic to reset the voltage, or the logic to enact the refractory period. And we don't necessarily know right now how to model the interaction between different biological constraints. How does the firing rate or limitations on the firing rate interact with adaptation? And this is all sort of starting to feel a bit ad hoc, like we're stapling things onto the model, and we don't necessarily know how the accumulation of all these features will interact with each other, and more importantly, do they reflect the actual biology? And further, when we look at actual rasters of neuron spikes, we'll find that they're more complex than just constant firing. There are many different kinds of firing patterns. And it's even including adaptation. There's more complexity going on in neuron behavior. So it would be nice if we could capture all of these behaviors with one model in a unified neuron model, but that is still mathematically simple than just, a reproduction of the neuron itself. And this brings us to the Itzekevich neuron. This is a mathematically simple, computationally cheap neuron model, but it can still reproduce diverse neural behaviors. And so we see some of these behaviors here. There's regular spiking, it's called intrinsically bursting, chattering, where we get bursts of close together spikes, fast spiking. Again, these are all different kinds of observations taken from biology that the Itzekevich neuron can explain. And Itzekevich put this model out in 2003, and it draws more heavily from biology than integrate and fire neurons. It takes inspiration from the fact that there are different ion channels or currents that lead to variable recovery times after a spike. In this model, we have two state parameters, U and V, and then we have four free parameters, A, B, C, and D. And so that's a total of 6 parameters to describe a neuron, which is more than integrate and fire, but still a fairly simple model. The two state variables are the membrane voltage and then the membrane recovery. And these are coupled via these two differential equations here, U prime and V prime, or dV dt, du dt. The recovery term U is meant to model the interaction between the sodium and the potassium channels in the neuron, because these are the ions that are involved when the neuron is creating an action potential and then returning to equilibrium. And then there's also a spike reset mechanism. So if V equals some threshold, then you do some reset based on the parameters C and D. And it's more complex than just the integrate and fire neuron, which is if threshold reached, then reset to specific value. And so these parameters, A, B, C, and D, affect the timescale for the recovery, and coupling the recovery to the voltage, as well as any after spike resets of the voltage and recovery. So more complex model, still fairly simple, capable of producing a lot more sophisticated firing patterns than we get out of the LIF. And which this is promising, because one of the things we want to do is explain different observations in biology. So if we can do it with this kind of a model, this increases our explanatory power considerably. However, there are still questions unanswered by both the integrate and fire and the Itzekevich neurons. For example, what is the biological meaning of the state variables? Right? We know what V is, it's the voltage, but what about all the other parameters in the system? And what happens when the effects of an input spike depend on the current state of the cell? Right? The way we have it right now, input from the input currents always change the neuron in the same way. And then what about studying the differences between an individual cell over time? With the integrate and fire neuron and with the Itzekevich neuron, the dynamics of these neurons are fixed once you pick the free parameters. And so to address these questions, we will in the next lecture address the Hodgkin-Huxley neuron model, which was designed as a bottom-up approach instead of a top-down approach to designing neuron models. And that is to say, it was taken from studying specifically the mechanics of actual neurons. And the hope is that by modeling all of the constituent parts of the neuron and putting them together, we will recover the behavior we observe experimentally. And specifically, we'd like to see the membrane potential trace out the action potential over time. And that is to say, not just say a spike has happened, but actually demonstrate the action potential that we see here. Right? This is the membrane potential. We want a neuron model that actually gives us this shape. So, readings, as given, are from Gerstner, and then project ideas for this course, or this lecture rather, is to implement. You could implement different kinds of neuron models and describe the differences in their behavior, subject to different kinds of inputs. You could research the neuron model competition and implement the training or testing procedure, or you could compare the runtime and memory usage of complex and simple neuron models. Which could help us evaluate what's the trade-off between the fidelity of the neuron and the ability to execute the neuron model in some reasonable period of time or memory, or put an upper limit on the size of the models you can feasibly simulate in your computer when trying to fit this experimental data. So that's it for this lecture. We've discussed neuron models with increasing levels of biological fidelity. We have discussed the breakdown between the synapse model and the neuron model and how these things relate to each other. And then in the next lecture, we are going to cover the Hodgkin-Huxley model, which is a much more biologically faithful description of what's going on in a cell. Thank you.